Hello friends. So, in this lecture we will learn about logistic regression. So, logistic regression is more popular for classification problems, unlike the linear regression where we are having the continuous dependent variable. In case of logistic regression we are having discrete output variable, means it will be having some discrete value. So, we will learn here in this lecture also this logistic regression we will see from the classification point of view. So, classification means like you are having some weather prediction whether it will rain yes or no. So, it is binary classification, you are having only two output values of the predicted variable, okay, that is your output variable or dependent variable, or you can say COVID positive or COVID negative, or you can say true or false, 0 or 1. Okay. So, all these when there are only binary output we say binary classification problem. If you are having more than 2 values for this output variable, then we will say multinomial classification problems. So, one example of that you can consider that whether a student is belonging to very good category, good, average, poor, like this. So, here I am having very good one value, good second, average third and poor 4. So, here I am having 4 classes. So, let me start this lecture from the binary classification point of view. Now, when we are going for this logistic regression, one can ask or one can question why not the regression we learned earlier for classification also, like why not linear regression or multiple linear regression or polynomial regression, or in a very confined way I can say why not least square method. Okay. So, in least square method what we used to do, we find our coefficient or parameters, let us say beta belongs to RP, which minimize the least square error or residual error, something like this, yi minus beta transpose xi and square of this, means this is the least square one, where this xi and yi are my given data points, I equals to 1 to n, and xi belongs to p dimensional space, means it can be p may be 1. So, I am having only one independent variable, or p may be some 10, 20, 30. So, that will be p is number of independent variables. Now, when I am solving this problem and so I am getting a continuous y. Okay. After getting beta I will get a model like y equals to beta naught plus beta 1 x 1 plus up to beta p x p. Now, whenever I am giving a new x here data, I am getting a value of y, okay, which may be anything between from the set of real numbers. But here for classification my problem is in especially in binary classification whether it is belonging to any of the two classes, let me say 0 class or 1 class. So, how I will divide this continuous values, whole continuous value, the whole real line into whether it will map to 0 class or 1 class. So, instead of that we have to think in terms of probability, and that thinking we are incorporating in the concept of logistic regression. Before going to logistic regression, let me learn about sigmoid functions. So, a sigmoid function is a mathematical function which has a S-shaped curve, something like this. You can see these three examples. All these three are sigmoid functions. The blue one is logistic function, the green one is hyperbolic tangent, and the red one is arctangent. This particular blue one logistic function we are going to utilize in sigmoid logistic regression. So, the function is defined by the definition of the function is like this. So, here S can be considered a function from set of real numbers to 0 1. Why 0 1? Because you take any value of x from minus infinity to infinity on the real line, you will get the value of S of x between 0 to 1. So, for example, when x is going to minus infinity, means it is having very large negative value. In this case, S x will tend to 0, because e raised to power infinity. So, 1 over very large value means it is going to 0. When x is plus infinity, my S x will tend to, so plus infinity means it is e raised to power minus infinity will tend to 0. So, overall S will tend to 1. So, this function is bounded between 0 to 1, that is very nice property. And when we say that a function is between having value between 0 to 1, means all value will be between, or the range of the function will be this 0 to 1, we are having a feeling of probability. Okay. So, that is first reason for using this function in logistic regression. Another nice property of this function is it is very well behaved function, very smooth, it can be differentiated any number of times, there is no issue at all. Okay. So, this is a brief introduction about sigmoid function. Now, come to our logistic regression. So, as I told you, we will see logistic regression for the classification application, for the classification type of application. So, it is basically a supervised classification algorithm. Supervised means a set of data is given to you, training data, where you are having input variables as well as output variables, and using this you have to train a model which can be used to predict some unseen input values for some unseen patterns. Okay. So, as I told you, in a classification problem, the target variable or output is y, can taken only discrete values, and in fact we are restricting ourselves to binary classification. So, this target or output variable can take only two values, 0 1 plus minus, true false, like that, good bad and so on. Okay. So, in this model what I will take? I will take two classes, 0 class and 1 class. Okay. So, these are my classes. So, now how this logistic regression becomes a classification algorithm? So, it becomes a classification technique only when a decision threshold is brought into picture, because this like the linear regression we will use the same kind of thing. Okay, y is a function of independent variables x plus some noise. Okay. But here y due to this sigmoid will be between 0 to 1. Okay. This y will be having value between 0 to 1, unlike the linear regression. And when you will put a threshold between 0 to 1, that let us say a threshold is, let me say 0.5. So, if the value for a given pattern value of the y is less than 0.5, it is belonging to class 0, and if it is more than 0.5, it is belonging to class 1. So, if you brought this kind of thresholding into picture, we can utilize it for the classification. Again, by default we can take this thresholding as 0.5, I will show you why, but it is again a very important aspect of logistic regression, that how to choose this threshold value for the better classification or for the better model. So, before going to details, let me give you some probability basics which we will use. So, let me have the definition of sample space, which is denoted by omega. So, it is the set of all possible outcomes of the experiment. Okay. So, for example, if you are having an experiment of tossing two fair coins, then what will be my sample space? So, you are tossing two fair coins, first one is having head, second one is also having head, first one is having head, second one is having tail, first one is having tail, second one is having head, and both are having tails. So, in that case this will be my sample space. Rolling a fair die, what will be the possible outcomes? 1, 2, 3 up to 6. Okay. Then sample space will be having 6 elements. Okay. Then I am having event space. So, the event space is the space of potential result of the experiment. The event space is obtained by considering the collection of subsets of your sample space omega. And when you are having discrete probability distributions, this your event space is nothing, okay. It is power set of the sample space. Then what is the probability? So, with each event A belong to my event space, we associate a number P A that measures the probability or degree that the event will occur. The number P A is called probability of occurring of event A, and this P A will be belonging to the set 0 to 1, and sum of all probabilities for all the events I, possible events I, will be equals to 1. So, for example, you are tossing a fair coin, okay. So, what is my sample space? Either head or tail. So, what is the probability of occurring head? It will become probability of having head is nothing, just 1 by 2 if coin is fair, and probability of tail is also 1 by 2. So, all both are between 0 to 1 and sum equals to 1. Now, let me give you the concept of random variable and what is my target space in case of classification problem. So, a random variable is nothing, it is a function, let me say x, from sample space to target space. So, for example, you consider the experiment that is having tossing two fair coins. So, my sample space is and now you define an event as the counting the number of heads. So, now what will be the value of XHH? It will be 2. What will be the value of HT? It will be 1 and it is equals to X of TH. What is the value of XTT? So, when both the coins are having tails, there is no head, that is 0. So, what is my target space? So, target space is nothing, it is having 3 possible values 0, 1, 2. So, these are nothing, just classes for my classification problem. Okay. Now come to the concept of logistic regression. Okay. So, first thing which I will say, instead of the function y equals to I was having alpha naught plus alpha 1 x 1 plus alpha 2 x 2 plus alpha p x p, like I was having in linear regression, which was nothing, I have denoted like alpha t x. Instead of this function, what I will model, the probabilities that y is equals to class 1 for a given x. So, let me denote it like this: probability of x equals to nothing, just p y equals to 1 for given x. Then I can define p x equals to, here in logistic model or in logistic regression. So, this I can define p x as the sigmoid function, that is e raised to power minus beta t x, sorry, alpha t x. So, if you see, I am defining in this way, or this I can write, if I multiply both side by exponential alpha t x, means in denominator and numerator, I will be having e raised to power alpha t x upon 1 plus e raised to power alpha t x. Okay. So, in the right hand side I am having nothing, just sigmoid of the alpha t x. So, basically I am using the sigmoid function instead of the linear combination of x 1 x 2 and so on. Now, what you do? You rearrange, what will be 1 minus p x? It will be 1 minus e raised to power alpha t x upon 1 plus e raised to power alpha t x. So, it will become 1 upon 1 plus e raised to power alpha t x. So, from here I can write p x upon 1 minus p x is nothing, just e raised to power alpha t x, or log of p x upon 1 minus p x equals to alpha t x, which is your alpha naught plus alpha 1 x 1 up to plus alpha p x p. So, what I was having y in my linear regression, here in logistic regression I am having this function log p x upon 1 minus p x. So, this left hand side is called logit of p x, or another name is log odds. So, now what I need to do, like we have done in linear regression, we have find out the parameters alpha naught, alpha 1 up to alpha p based on the given data. Here also we will do the same kind of thing. Okay. So, let me come to the process how we will do it, how we will estimate alphas, alpha naught, alpha 1 up to alpha p. So, I am continuing with logistic regression. So, given samples, let me take my data is x I and then y I is the true classes which belongs to, let me say, my input variables are p variables into output is either 0 or 1 and I is 1 to up to let us say n. So, this is the given data. I am having set of input variables for n number of patterns, means n feature vectors and their classes, whether a particular pattern is coming from 0 class or class 1. Now, what you do? My model is log p x I for a particular pattern upon 1 minus p x I equals to nothing, just alpha transpose x, and when I am doing a particular pattern x I, so this x will be x I and that is true for I equals to 1 to n. Now, I need to estimate alpha naught, alpha 1 up to alpha p, okay, all these coefficients. Okay. So, let us say I am defining this set by the alpha cap, this vector, okay, the coefficients. So, here we need to estimate these and we use the technique of maximum likelihood estimation for it. So, what I will do? I will define the likelihood function of alpha, capital L of alpha, which is nothing, just all I where y I belongs to class 1, product of the probabilities of those into I when y I means class is 0, all patterns from 0 class, and 1 minus p x I. And why I am doing 1 minus p x I? Because you know here I am having only 2 class. So, if p x equals y equals to 1 for a given x equals to alpha, then probability of the same pattern being in class 0 will be 1 minus alpha, because total sum is 1. So, I can write it in a more better way, I equals to 1 to n p x I raised to power y I into 1 minus p x I raised to power 1 minus y I. Now, we will maximize this L alpha and we will find out the alpha which maximize this, means this function, that will be my optimal choice of the coefficients alpha. So, now you can see here all these are probabilities and they are positive values. So, it is maximizing a function is the same as maximizing the log of a function, because it is positive and so monotone increasing. So, what I will do, instead of maximizing this particular function, I will make use of I will maximize the log of L alpha. So, what I will do? I will define L alpha which is nothing just logarithm of capital L alpha, and when I will take the log of this, I can write in a more better way in summation form instead of those power y I log 1 minus, not 1 minus log p x I and plus 1 minus y I from this term. So, in log log a raised to power b can be written as b log a. So, I am using the same y I log p x I, and this product will change into summation after taking log 1 minus p x I, or we can rearrange it a bit. I can write I equals to 1 to n, and then I am having y I as out, and then I will be having log p x I means this term, and then from this term I can have minus log 1 minus p x I, just coming y I times this one, plus what is left log 1 minus p x I, or in a more better way I can write it I equals to 1 to n y I log a minus log b, I can write log a upon b. So, p x I upon 1 minus p x I, and what is this? This is log odds of p x I plus this term log 1 minus p x I, and you know this log this one, this particular term is nothing, just if you see the previous slide, this is equals to alpha t x I. So, let us plug it here I equals to 1 to n, what I will be having y I alpha t x I minus log 1 minus p x I, and I have to maximize this function. Now, like the least square one which we have seen, we are having a closed form solution in terms of pseudo inverse or like that. Here we do not have closed form solution, because for maximizing I have to do del L alpha over del alpha equals to 0, the necessary condition for the existence of maxima or minima, and then I will not be able to get a closed form solution. So, what is the solution? I will apply some numerical optimization technique, which you will learn very soon in optimization module of this course. So, I will use numerical optimization technique to maximize this function. One of the choice may be gradient descent. Okay. So, by applying that numerical optimization, you can calculate the maximum value, means those alpha which will give you the maximum value of this log likelihood estimator, and this is the overall process of logistic regression. Okay. So, what we have learned, instead of using y as a linear combination of different features of the data, we are using the sigmoid function. From that we are converting it the log in the probabilities, and log it of the probability of x being in class y being in class 1 for a given x equals to e raised to power that is alpha transpose x, that linear combination. Okay. And then we are modeling it into for finding the alpha, those coefficient, estimating those coefficient, we are converting it into log likely maximum log likelihood estimation problem, which does not have a closed form solution. So, what we are doing? We are using a gradient numerical optimization algorithm to find out the optimal values of those coefficients. Once you are having optimal values of those coefficients, what will happen? For an unknown pattern, let us say a new x star I will say x I star. Okay. So, it will be something like this. Let me write it x I 1 star, x I 2 star, x I p star, okay, like this, because my x is p dimensional vector. Okay. So, for this you do not know y I, whether it is 0 or 1. So, what you will do? You will calculate, because now you know the alphas, you will calculate this value alpha naught, alpha 1 x I 1 star plus alpha 2 x I 2 star plus alpha p x I p star. From here you will get some value. Okay. Let us say this value is m. Okay. This equals to m. Now, what we will do? Okay. Based on this m, I will calculate the value, okay, y, and y will be nothing, just 1 upon 1 plus e raised to power minus m. Now, this y will be a value between 0 to 1, and then the pattern x I star, which you were having unknown pattern, I do not know the class, belongs to class 0 if this y value is less than 0.5, otherwise this I x I star belongs to class 1 otherwise. Okay. So, based on this value you can make the prediction. So, what I am having? I am having x here, y here, okay, that will be the this kind of y, and I am having this curve. Okay. And here at so it is 0, it is 1. So, at 0.5 you are having this thresholding. Okay. So, if x is mapping, let us say this is my unknown x is mapping here. So, it is belonging to class 1. If my x is this one, it is going here, which is less than 0.5, it is belonging to class 0. So, all data points those are coming before this will be in class 0, and those are coming after this, all these will be in class 1, and that is the simple concept of logistic regression. Although that theory which I have told you is having a bit like new terms, maximum likelihood estimation and all those kind of things. So, we have learned the what is logistic regression and what is mathematics behind this logistic regression in this particular lecture. Okay. And we have restricted ourselves for binary classification problems. Although for multiple class, if class value is more than 2, you can still use logistic regression, only you have to add some additional thing, like one is one hot encoding for modeling the target space, and the second one is instead of this logistic function, because then your it will be vector valued your target classes, output will be vector valued. So, there you have to use softmax function. Okay. So, you can see those two concepts, how to convert logistic regression or how to apply logistic regression for multiple class problem. So, with this let me close this lecture. Thank you very much.